So now I give the floor to Ronan, who will moderate the second part.
Good afternoon, good morning. So the next talk is about explosion discrimination, and the title is Limits of Explosion Discrimination for Monitoring Efforts with Machine Learning. And this is given by Luisa Barama from Lawrence Livermore National Labs. Luisa is online, so she will be able to answer questions later on. The floor is yours, Luisa.
Please play.
Hello, my name is Luisa Barama. I'm a postdoc at Lawrence Livermore National Lab, and today I'm going to talk to you about ongoing work on global and regional underground nuclear explosion discrimination with machine learning, and ways that we're looking to improve existing models and combine existing models by adding seismology-led and physics-based features. The three goals of the work that I'm showing today was looking at the transportability of global models to regional distances, making use of legacy underground nuclear explosion data, and looking more at the impact of adding features to our training data. I also want to apologize. My slides are in the format for a poster. There was a bit of a miscommunication of whether or not my virtual presentation would be a poster or oral slides. So my presentation is in a poster format, but I've zoomed into certain sections to hopefully make it easier to follow. So I thank you for your patience on that. So let's first take a look at the data. Plotted here in red are the underground nuclear explosions used in the training data set. All of the holdout underground nuclear explosions are in yellow, and all of the triangles denote seismic stations with color denoting what institute that data is sourced from. Now, to generate this list and to compile this data, we first started with a digitized comprehensive list of 2,174 declassified nuclear events reported globally. These two reports we sourced this information from were from the Defense Research Establishment and Stockholm International Peace Research Institute, and a report from the Department of Energy in the United States. For the North Korean tests, we used the USGS reported origin time and coordinates. We only wanted to include underground events, so that narrowed down all of our explosions to 778 events that were detonated either in shaft, tunnel, gallery, mine, or buried, and also had waveforms available. Then we made this training data set, reformatted in a way that's easy to use not just for seismologists, but also data scientists interested in exploring machine learning for this problem. And we published this data set in 2022, and it's now available on GitHub and Zenodo. On the left-hand side here, we have two example waveforms. The top is from an earthquake, the bottom is from an underground nuclear explosion, and the white trace there is just an example of what a 1-minute cut of that segment looked like. For development of our global underground nuclear explosion discriminator, we tested with a variety of different window lengths. We finalized on 20 seconds long. And we found high accuracy when both training on only historical data, which included formerly analog and then digitized data, and applied it solely on the more recent North Korean tests, and vice versa. In order to fine-tune the global discriminator that included a lot of teleseismic data, we narrowed the distance range down to 20 distance degrees. So plotted here, we're just showing the distribution of data with station epicentral distance degrees, and we cut off the range of distances to 20 degrees, and we're just showing here that we were able to do that without removing too much of the data that we had. So there's a bit of limitations when we're looking at explosion data. There's, especially for underground nuclear explosions, there's many repeated test locations and emplacement conditions. To address this limitation, the training and testing data, we separated it by unique source and location so that we weren't repeating on a lot of different sources. We treated those unique, location and station pair were really just the emplacement condition testing locations. We didn't want to train on the same location tests and then test on those. So we're trying to remove that bias. Oops. We have data specifications. We used distances from 5 to 20 epicentral distance degrees. P-wave seismograms that range from 20 to 60 seconds. We ended up, for the final model of the results I'm showing today, we used 20-second seismograms, and we bandpass filtered from 1 to 5 hertz. For each of the waveforms included in training, we had corresponding features that we calculated. Those included the dominant frequency content of the trace and signal-to-noise ratio at 2 different frequency bands, a high and a low. We included polarity and the P-wave decay or slope. So our pre-processing and signal-to-noise ratio already does decrease the number of samples that we can include in training, but also limiting data to only regional distances also decreased our training data samples to around 10,000, a little less than 10,000 samples. To increase this, we used data augmentation, and what we did was, rather than have a fixed point in time within our 20-second window of where the P arrival is, we allowed there to be variability and flexibility of where that was. So for a single trace, we had 3 different iterations of that waveform with a randomly selected point in time within the window of where the P arrival is. So this is a way to really boost the number of training samples that we had and stabilize our training. Now we're going to take a look at our model architecture. So we combined our 2023 global convolutional neural network that was a 3-class output. So output of earthquake, nuclear explosion, or noise. Then we combined it with the 2-branch model from Kong et al. In 2022, where they combined the powerful features of a convolutional neural network with physics parameters and had a 2-class output where they focused on chemical explosion or natural earthquake at more local distances. Now, convolutional neural networks can be applied to 1D time series by sliding this 1D convolutional filter across an axis to detect local patterns, for example, peaks, dips, oscillations, or features that are like an impulsive P arrival for an explosion or a non-so-impulsive arrival of an earthquake. And we can pool all of these together into a dense layer that then aggregates all of the learned features to perform regression or classification that are shift invariant, which makes them really useful for discrimination and classification tasks. So when we're looking at the 2-branch model from Kong et al. On the right-hand side, the blue dotted box is the deep learning branch, which takes in waveforms as the input, with the convolutional neural network layers as the hidden layers, and a fully connected layer to flatten out the features. The green box on the bottom contains the physics-based features, where we include all of the features that we're including alongside the waveforms. The features from these 2 branches are then concatenated and pass to another fully connected layer to make the final decision of explosion, earthquake, or noise. So looking at the results of our model, we plotted here as the earthquake accuracy in blue and underground nuclear explosion accuracy in orange. For the global model, where we had a large range of distances, teleseismic and regional all combined together, our results center around 90%. For when we're incorporating our waveforms and features, we improved that model accuracy up to centering around 95%. And when we focus down to just regional waveforms, then we have limited improvement of the model up to about 96%. We can kind of explain this with there's more variability in the waveforms that are across a large distance range, to teleseismic range. And so focusing down to just the regional waveforms, we have more consistency across our measurements. But on the whole, this is an encouraging result, so showing that incorporating additional features does improve our model robustness. And for our ongoing work, we're evaluating the impact of additional component data, such as multiple frequency bands and quota envelopes, to further enhance our model performance beyond single frequency band or raw data approaches. We're also comparing conventional methods of explosion discrimination, like P to S ratios, and seeing if there's advantages of machine learning models when these conventional methods have less confidence results, or where our classification confidence is low. But with that, I want to thank you for your time, and I'm happy to take any questions during the live session, or feel free to email questions to me at my last name, Barama1 @llnl.gov. So thank you for your time today.
Thank you very much, Luisa. We do have one question, and the question that we have is, would you expand a little bit on the data augmentation process?
Yes, of course. So the data augmentation that we did here was actually pretty simple. We narrowed down what length of window we wanted to train the model of for all of the seismograms, or all the time series data. And so we just, set a random, built a quick random algorithm to say, okay, we need, from this one single trace, we then allow the P arrival for the earthquake or underground nuclear explosion to arrive anywhere within that window, allowing for at least 5 seconds of signal. So that meant for a 20-second window, it could arrive. You could have the P arrival at up to 15 seconds. So we had 5 seconds of P arrival signal, but it could occur anywhere within the window. I think we had a buffer of 2 seconds. So it's from 2 seconds to 15 seconds that P arrival could arrive anywhere within that window. So this is actually pretty simple data augmentation, where for each single trace, we had 3 different cuts of that data. So, what we see here is that this reduces the overfitting. So by exposing the model to this wider variety of data, this augmentation can then prevent it from memorizing specific characteristics of the training data. So here, if we had, before this, we had set that the P arrival was always at 5 seconds within the window, or 10 seconds if we were using a 1 minute long seismogram. And this actually, when we did see that, for one, you have less data to train the model on, which makes it a little less stable. But then when we applied the model on a continuous data stream, we actually saw a lot of flipping of the model predictive confidence of whether or not it was an earthquake or explosion. There was a lot of variability, especially right before the P arrival. And when we did do this applied data augmentation, you're preventing the model from learning that, at 5 seconds is when I should see a signal. So you're actually, you're kind of preparing the model for more diverse scenarios. So you're making the model better, but also at the same time, you're stabilizing the training also by kind of increasing this kind of artificial increasing of your data. And there's other things that we could have done, is also adding noise into the data. So there's other things that we could do to make small modulations to the training data to also boost the amount of data. I hope that answers your question.
Thank you very much, Luisa.
Yes,
Thank you.
Luisa, indeed. I mean, it's very robust, the system that you are applying. And we got another question from the audience that is on the same page. So they thank you for your interesting talk. And I will read. I was wondering what common features across all the training waveforms allow your algorithm to identify a new event from a different location. So what common features across all the training waveforms? Luisa, you're muted.
Oh, I am so sorry. I had muted myself again. Thank you for your question. We actually had some pretty simple features. So the convolutional neural network part of the model architecture identifies the parts of the stream that are unique and also consistent for each training division. So there we have whatever the machine is able to recognize using those convolutional filters. So identifying what maybe is harder for us to identify that is consistent and unique across all earthquakes, P arrivals, or all explosion arrivals. And then the features that we added in for right now, we actually, for this model, we didn't include P and S ratios. We were focused really on trying to focus on the P arrivals, but we were also looking at the signal to noise ratio and the ratio of energy in the seismogram at lower frequency bands compared to those at higher frequency bands. And explosion data is often more emergent in the explosion data at higher frequency bands. Then we're also looking at the coda slope and then the overall energy. So that's the square of the velocity seismograms of that P arrival. So those were the features. I actually don't have an answer for which features were the most useful for making the determination, but that's definitely something in our continued and ongoing work of using a random forest and doing some feature ranking to see what's the most useful in making our determinations. I hope that answers that question.
Thank you very much. I think we will. Thank you very much for your answers, Louisa.